In this video, we're going to talk about the Kohler Illumination system. So this is one configuration of lenses and a lamp that is commonly used in light microscopes. So particularly what we're going to be looking at is those in transmission light microscopes. So this is the arrangement that we're going to look like. But again, you can use this for reflective too. It's just a modification to this. So this one system can be set up in two different ways. And so we're going to start by looking at the conjugate field planes. So this is a particular arrangement that we use for image formation. And so what I'm going to do is I'm going to sort of draw from the bottom up to kind of show you from the lamp, which we just talked about, all the way up to the eyepiece and your retina, how this configuration works. So let's start with it. All right, so down here, I'm going to draw my lamp. So this is my lamp down here, just a box. I'm not trying to be fancy with it or anything. From the lamp, so this is my lamp, the light goes through a lens. So it goes through the kind of the first lens in this arrangement. And so this is the collector lens. And so it goes through this collector lens in order to become convergent to a specific plane. So if I think about my light going through the lens from the lamp, it converges, like we've seen before, at a point behind this collector lens. And that's important because this is going to be what we call the front focal plane for the condenser lens. So that's the next lens that we're going to talk about. So at this point, we also tend to have an aperture. And so I'll just sort of draw that, but we'll come back to it in a bit. So this is how I'm drawing apertures. All right. So I'll draw it there at the focal point, but we'll come back to that. All right. So it's converged. Now it becomes divergent to our condenser lens. So our condenser lens is up here. So these ellipses are just representative of lenses. And so this is my condenser lens. And again, we talked about this briefly in the overall construction of the light microscope. That's what collects and produces a light source onto the specimen itself. So basically, the light becomes divergent and goes to the collector lens. Or sorry, the condenser lens. So the condenser lens, its job is to take the light that we have, from the lamp, the collector, through this aperture, and its job is to produce a small point on our specimen. So I'm going to draw this as our specimen. So that's our specimen, and the job of the condenser lens is to focus that light onto a point in the specimen. Right? So the idea here is we've taken the light from the lamp, the collector lens focuses it to the front focal plane of the condenser lens, and then the condenser lens takes that divergent light and directs it at a small area of interest on our specimen. So that's what we actually want to look at, is that small area where the light is being concentrated. So this has gotten us all the way to the specimen, right? So this is kind of the part that we typically haven't talked about. We've talked about the other side. But the interesting thing is the other side of the sort of the light, the ray diagram that we have is basically the same. So we have the light, it diverges from the specimen. We have a lens here, this being our objective lens. So this is the one we're familiar with. And then the objective lens takes that divergent light and focuses it. So we have light that focuses to a point. And this is our eyepiece. So it focuses it to the eyepiece, or ocular. Also, I'm going to draw it in, but we'll talk about it in a second. We have another aperture here at the eyepiece. So this is our image plane. Right? That's where the objective lens is making this light converge to the image plane. So this is where we're forming that magnified image. And the eyepiece is taking that convergent light and producing it for the eye. So this is our, again, the retina we showed as the back. Let me just kind of show that off. So we have the retina and the eye, as we kind of think of it as an eye lens. So that divergent light goes to the eye focuses it or converges it to the retina. And then again, we don't perceive the eye in the retina, we perceive it in front of the eye, away from it as a virtual image. All right? So this is the configuration that's used for image formation. Right. So, and the key here, and the reason we call it conjugate field planes is because if we think about the ray diagram below the specimen and above it, they have the same sort of pattern of these two lenses in the way that the light corresponds with those lenses. So it's conjugate on either side of that. So that's why we call it a conjugate field plane. And that's the sort of arrangement we have for image formation. And so that's what's important for image formation. However, we can also rearrange things with the same Kohler illumination system such that we can align the microscope. So kind of a calibration mode, so to speak. And so this is the conjugate aperture planes. So we're going to look at a different variation of the system that we have here. So let's go back and go through that system again. And I'm going to draw you it on this side, starting with the lamp. So if I draw it in the same place, it means it's the same thing. All right. So we're going to have the components are all the same. So we have another collector lens. We have, again, that aperture that I talked about at this point. So the aperture hasn't changed in this diagram. I forgot to draw. I apologize. I forgot to draw it over here. But we actually have a aperture set here, and I'll come back to this in a second. But let's start to look at it. So in this case, what happens with this type of diagram is instead of light here that we have that sort of goes through this collector lens, converges to this point, what we have is we actually have divergent light. So we start with a point, and then the light diverges to that lens instead of converging to that lens. So what that does is that makes this divergent light converge to a point up here. And so where that focal point is now is where that additional set of aperture is, the additional aperture here. So this is referred to, and I'll draw it over here as well, and point to it. This is the aperture diaphragm. So this is the aperture diaphragm, and it's at a point where that light converges in this mode. All right. We still have the condenser lens above it, and the light's going to diverge towards that lens. We still have the specimen in the same place. And so in this case, the light is actually very broad and divergent at the specimen. And then the objective lens condenses it at a point up here on what we call the back focal plane of the objective lens. So this is the back focal plane. So this would be the front. Just for reference, this would be the front. In that case, so we're just referencing the objective lens. All right, so it converges to a point here, and again, this is where we have another aperture. So in this mode, it converges to a point here, and we have an aperture at that back focal plane. So I'll put it up here as well, back focal plane. So we have an aperture in this back focal plane. All right, so from that point, we have the eyepiece left and obviously the eye to consider. So the from the back focal plane, the light diverges to the eyepiece, and then it starts to converge to the eye, but it's actually converging in the middle, and then it diverges at the retina. So you can see that because of the initial form of light and it being divergent, this affects the overall progress of this, and you can see it's very different from the type of image. So this is not used. This is not used for image formation. It's used to align the microscope because of the way that it's set up with these apertures. So we can use these apertures to kind of align the microscope in a way that will help us when we're using it with the conjugate field planes. So this is basically illuminating the, or it's the light is becoming convergent in these aperture planes. So that's why we call it conjugate aperture planes. Right? And so those again are going to be similar on both sides. It converges at this plane and the front plane here and the back plane here. And again, it's for alignment. All right, now that we've sort of gone through the overview of this ray diagram for the Kohler illumination system, I want to focus a bit more on these aperture or diaphragms that we're talking about. So I didn't fully label this. So the first one I drew here, this aperture or diaphragm, this is known as the field diaphragm. So we have the field diaphragm here, again used for adjustment purposes, and we also have the aperture diaphragm. So these are the two I want to talk about in a little bit more detail. So let me start with a new page here. All right, so the field diaphragm. So this is, as you saw in the previous diagram, located at the focal plane for image formation. So again, let me go back to this real quick. You can see the field diaphragm here. This is where it converges. So this is the, this is the image plane, or this would be conjugate to the image plane. So it's the focal plane on the front side. So, I showed you the location, but I want you to also think about what its purpose is. So the purpose here is to alter the diameter of the area of the specimen illuminated. So it basically allows us to affect the area on the specimen that is illuminated. So if you if you're looking at the image and you see a diaphragm, so if you see something in the image itself, right, restricting the view, then this is the field diaphragm. So sometimes it's actually seen. So if we have like a microstructure here, this is an image you're looking through the eyepiece, and so you see all these features on your image, and I'm gonna kind of shorten it. All right, so that's our image, and then you see this thing around it, and it's black out here, right? That's this diaphragm. This is a field diaphragm. So we can sometimes actually see this diaphragm when we're looking at the image. So it restricts the area of view and blocks light, scattering light. And the reason we do this is because that scattering light can cause glare and image degradation. If it enters the objective lens. So basically we want to eliminate this glare, this scattering light that may cause glaring, because if it enters the objective lens and eyepiece, it causes a degraded image. So that's the portion. That's the reason we have this field diaphragm. All right. So now I want to talk about the aperture diaphragm. So just refresher here. If I put the drawing back up for this, we see that the aperture diaphragm is located on the front portion of the condenser lens, and if we go over to our drawing here, this is where in the conjugate aperture planes we have convergence on this place. So this is the aperture diaphragm. All right, so let's look at what this does. So again, you just saw this, but it's located at the focal plane of illuminating light rays. All right, so that's where it was located. You saw that. What it does is it defines and limits the aperture angle. So that was alpha that we talked about, right? So we've already kind of talked about the purpose of this diaphragm because we've talked a lot about what aperture angle does, and numerical aperture as an extension of that. But this is what actually can adjust the aperture angle. So we can use this aperture diaphragm to modify this angle for us. And so that will in turn affect the resolution and depth of field. So capital R for resolution, D sub F for depth of field. And so just a side note here, we can't see this aperture like we could the field diaphragm. So that's kind of the differences we have between those two. All right, so we've talked a lot about this Kohler illumination system and just recently the diaphragms and how that can affect the images. So now I want to ask a question related to this figure here. So this is figure 1.14 in your book. And so you can see that it's titled Effect of Aperture Diaphragm on Specimen. And so A over here on the left is where we have a large aperture. And then B is where we have a small aperture. And so the image is a little sort of grainy in your textbook. And you can see here, both of these were taken at 500x. So a lot of the image quality is because it was printed in our book. But what I want you to do is, based on what we know about the aperture, I want you to see if you can, based on our sort of principles that we know about light microscope at this point, what do you think the effect should be of a large and a small aperture on the image, right? So think about, based on theory, what that effect should be, and then obviously take a look at these images and see if that sort of relates to what the differences are in these two images. So do that. That will be found in your quiz. So do that, take a look, and then we'll come back and we will talk about this. All right, now that you've had a chance to look at that quiz question related to this and what we would expect from a large and a small aperture as you see it in A and B respectively, let's discuss what that should be. So a large aperture is going to have a large aperture angle, or alpha, so a large A, alpha. That's what we can kind of expect from the theory, right? So we've looked at a lot of aperture angle. And so if we look at those equations, for example, resolution and depth of field, what we see is that having a large alpha will give us better resolution. But as we know, the trade-off there is that it lowers the depth of field. So large aperture, so A, based on the theory, we'd expect better resolution, but the depth of field would be lower. And then conversely, if we have a small aperture, we're going to get a small aperture angle, alpha, and that's going to give us a larger depth of field, so a larger range of z-axes over which it looks sharp, the image looks sharp, but the resolution is going to be reduced. So that's what we expect to see. And so now I want us to kind of tie it to the images that we actually see. And when we look at these images, I don't know about you, but I don't necessarily see an issue with better or worse resolution or depth of field in these two cases. They're actually fairly similar, but I would say maybe it looks more like it's a contrast difference, right? And so you can also kind of consider that as well. And so to me, even though a large aperture will give you better resolution, and a small aperture will give you a larger depth of field, it doesn't necessarily mean that those are the only things to consider, right? So it looks like, for example, if you kind of look in this region, we see a bit more contrast between these stripe regions, which gets blocked out here because the contrast between the features is less. So the kind of point I want to get across here is that we don't always need the best focus or resolution to obtain the best images. We often need to think about other things: contrast, brightness, all those the things that we've looked at in these cases. All right. So we've talked a lot about the Kohler system up to this point, and I want to give you some advantages of why we actually use this. Why do we go through the trouble of having a system the way we do? So our main advantages, and number one, and obviously this is going to be very important, this system produces a bright and even illumination. So we saw with the various lamps, right? The intensity of light is going to be important, right? And we also saw earlier when we talked about contrast, right? Contrast, the thresholds that we require for contrast go down if we have very bright light. So we want it to be very bright, and also even is important, right? Over the entire specimen we're looking at, this system provides even illumination. So the brightness is going to be even across the specimen that we're looking at. So that's going to be definitely important for this system. So we don't want any differences in illumination. So the other part of that, what that offers us, is that even if we have an irregular light source, so if our light source isn't perfect, so irregular and causes non-uniformities, the system that we have here with the apertures and the lenses still obtain bright and uniform images. So it allows us to have less dependence on the light source itself. All right, so basically this is going to be a huge component of why we use this system. But also, the positioning of those two different sets of conjugate focal planes at specific locations along our optical axis So basically the positioning we have here with these two different sets of conjugate focal planes at specific points in the optical axis, this is a strict requirement for maximum spatial resolution. And therefore optimal image formation. So the fact that we can adjust this, positions of those planes at specific points, is going to give us is the requirement for maximum spatial resolution. So those are the two defining characteristics of this Kohler light system. All right, one last thing to mention in the illumination system is light filters. So I just wanted to briefly talk about this. So light filters, their purpose is that they can be used along the light path to control wavelength, and we used lambda for that, or intensity of illumination. In terms of light filters, we can have two types. Color filters. So if we can control the wavelength and intensity, therefore we're going to have two types. So color filters. This is commonly used to produce a broad band of wavelengths. We can use them they're used by matching the color temperature that we talked about before of the light to that which is required. So if the photographic films need a particular color temperature, then this can be used. Also, be able to increase contrast. So a couple functions there. So that's color filters. All right. So now the other one that we want to talk about, number 2, is interference filters. So that's the second type that we have. So these, what they do is offer sharply defined band widths. So instead of a spectrum, it's just a specific bandwidth. And commonly encountered in fluorescence microscopy. So we haven't talked about this specific type of light microscope, but we will talk a little bit about it later. So specifically for that when it's required. So this won't get as much attention just because we won't talk as much about fluorescence microscopy.